Okay, so now we're going to talk about congruence and transformations. So when we talk about identifying congruent figures, we need to see if two geometric figures are congruent figures if and only if there is a rigid motion or a composition of rigid motions that maps one of the figures onto the other. So we want to recall that translations, reflections, and rotations, as well as any composition of these transformations, are rigid motions. So congruent figures will always have the same size and shape. So you can see here that our congruent figures, all of these, no matter how they've been turned or moved, they all have the same size and shape, so they are in fact congruent. But over here, these are not congruent. These may be similar, and we'll talk more about that in year 2, so as your sophomores. And then these over here, this one you can tell are very different. So a dilation, remember, is not a rigid motion, and therefore it would not create a congruent figure. So over here on the grid, go ahead and take a moment to pause the video and match which ones are congruent figures. Okay, so when we talk about congruence transformations, another name for a rigid motion or a combination of rigid motions is called a congruence transformation. Because the pre-image and the image are congruent. Again, we're going to think about the words rigid motion and congruence transformation are interchangeable. So compositions of two reflections will result in either a translation or a rotation. So a composition of two reflections in parallel lines will result in a translation, and compositions of two reflections in intersecting lines result in a rotation. So here we're talking about reflections in parallel lines. So I have two parallel lines, K and M, and we're reflecting BA through this mirror line or line of symmetry, line of reflection, over here to B prime, A prime, and then we're reflecting it over M to get B double prime, A double prime. So you can see that really we've just taken BA and we've translated it over to B double prime, A double prime. So this would be the same as our translation. So if this occurs, A double prime is the image of A. So the segment A double prime will be perpendicular to both of those parallel lines. So as you can see, when I move this point over to here, you can see that they are perpendicular. And then the distance from A to A double prime or B to B double prime or any point to its double prime, we know that this distance is D. And so if it's being moved to here and then over, that the distance entirely from A to A double prime is 2D. Now when we talk about reflections in intersecting lines, lines K and M intersect at point P, so it's right there at point P. A reflection of A, B, and K is going to rotate it up here. You can kind of see that it's been rotated slightly about point P. And then if it's rotated, or if it's reflected again to A double prime, B double prime over line M, we're seeing that we've actually taken AB and we've swung it around so it's over there at B double prime. So this would be the same as a rotation about point P. Now the angle of rotation, so again, between these lines here, between M and K, the angle is X. When I'm rotating A to A double prime, that angle of rotation is 2x degrees. So it's double the angle between M and K. So if you'd like, you can go ahead and look at these three down here. These are some examples. You can think about how they were moved, what they could be. For example, to get in the center one, P to P double prime, I reflected it over K and then reflected it over M, or I just translated it the distance of 2D. And then you can talk about this one being a rotation and think about how you could get A, B, C, D, that parallelogram, to be down here at the green one.